All right, so today we're going to talk about parameter estimation. So, as usual, we assume that we have some population, and we are going to sample from this population, but the population is described by some particular random variables distribution. So it's described by some distribution, which we think of as described, for example, by a probability distribution function. So some PDF little f of x. And we're going to grab some sample of n independent and identically distributed random variables. So IID, random variables, x1 through xn. And again, the assumption is that all of these have the same probability distribution f of x. Okay. And so, for example, if I thought about all these measurements together, they have some joint distribution function, which, because they're independent, is the product of the individual distribution functions. E.g., we have the joint distribution given by little f of x1 through xn, which is just the product of each of these same f's applied to the little xi, I1 through n. All right, so this is the situation, but secretly this function little f depends on some unknown parameters. So we might imagine that if our population is normally distributed, we might have some parameters, in this case the mean and the variance, which describe our particular function f of x. And so really the goal is to try to estimate, figure out what these parameters are. So f of x is really some f of x comma theta, or maybe theta 1 through theta r, or some list of thetas. Theta is some unknown parameter. And our goal is to find theta. Or at least with some amount of certainty, so to speak, find theta. And the basic method that we'll describe is to design new variables. This will be capital theta hat. Should make that more obviously capital. So this is supposed to estimate our parameter. Our parameter theta. The new variable is going to be some function of our observations. So it's g of x1 through xn. And then what we want to do is we want to just quantify in various ways how well our random variable approximates our parameter of interest, little theta. So of course we've seen some examples, and I think the two most important examples are probably the case where the parameter of interest is a mean. The thing that the random variable that we're using to approximate that is our sample mean. We could be looking at the variance, and then we might want the sample variance s squared to try to approximate that. So such a random variable we'll call an estimator, or really I should call it a point estimator, because because we are using it to describe not a range of possible values that our parameter theta could be, but we're trying to guess a specific value based on the value of the estimator. Now, the more we understand these random variables, theta hats, the more we might be able to build, for example, confidence intervals and other things, as we've discussed to some extent previously for our parameters theta. But right now, let's focus on just the random variable itself and try to understand how well its particular values are predicting the parameter theta. So there's a number of ways to think about that. So what are we looking for in our estimators? There's a few things that we look for, but today I want to focus on a couple of things. The first of which is the notion of being unbiased. So definition first, an estimator, a point estimator I should say, theta for a parameter little theta is unbiased if its expected value as a random variable is just the parameter theta. So for all possible values of theta. So we should put that in. I mean, the point is, like, one strategy that you might use, one estimator that you might use might perform very well for certain ranges of theta, but not actually give you the right answer for other values. We don't want to look at that. We want something that works for all values of theta. That's an unbiased estimator. Let's give some examples. So if you have a let's say you have a okay, first example is the most simple I think we can probably imagine, which is the sample mean is an unbiased estimator for the population mean. So let's just see that real quick. So how would you work out the estimated value of this? Well, let's just do it. So this is, by definition, you take the sum of your samples divided by n. I'm looking at the expected value of that. And of course, this is a linear process. So this is the same as the expected values of each of these operators divided by, of each of these random variables divided by n. Expected value of each one, these are independent, identically distributed ID random variables. So you just get, for each of these guys on the top, so the sum from I equals 1 to n of the sample mean. They all have the same mean mu divided by n, so I have n mu's divided by n, and that's mu. Okay, not a big deal. There we go. Okay, and next let's take a quick look at the sample variance as an estimator for the variance. So we'll look at S squared as a point estimator of sigma squared. So let's just go ahead and take a look at this. How are we going to do this? We're going to look at the expected value of S squared. So this is the expected value of this expression, 1 over n minus 1 times the sum of the difference between the variables and the sample mean from 1 to n. Okay, looks like this. So we get 1 over n minus 1 expected value of this guy, sum equals 1 to n xi minus x bar quantity squared. Okay, and there's a few different ways to do this, but let's go ahead and FOIL this out. It's going to take a little bit of computation. We're going to have to work a little bit just to do a little bit of algebra and arithmetic, but we'll get through this. So let's see. Sum I equals 1 to n. So now I have the xi squared minus 2xi x bar plus x bar squared. Okay. And now this expected value is going to break up, and well, I guess first before I do that, let me just rearrange the sum a little bit. So I got the sum I equals 1 to n of the xi squareds minus 2x bar sum I equals 1 to n of the xi's plus sum I equals 1 to n of the x bar squareds. Okay. Now, of course, this guy right here, this is n times my sample mean, so I actually have a slightly nicer expression there. The expected value of sum I equals 1 to n xi squared minus 2n x bar squareds. And then this last term is n x bar squareds. So altogether, I really got 1 over n minus 1 expected value of, let's see, what is this? Sum I equals 1 to n xi squared minus n x bar squareds. Okay, so now let's just remember what happens when you take the expected value of the square of something, right? If I were to take, let's see, if I were to take the expected value, let me just call it like some generic variable of x squared, then this is sigma for x squared plus the mean of x squared. And in particular, we know that the variance of x bar is actually the variance of x, which is our just population variance, divided by n. And yeah, so let's just go ahead and start working with this now. 1 over n minus 1, sum of the expected values of all these xi squareds minus n times the expected value of x bar squared. Okay, so that's 1 over n minus 1. The expected value of xi squared is the population variance plus mean. And of course I have n of those, so maybe I should scoot that over a little bit, because I'm taking a sum I equals 1 to n, so I have n of these guys. And then I have n of a similar expression, but now involving these guys. I guess I didn't write the mean down as well. So the mean of the sample is just my population mean. Okay, and then let's see, what do we have here? So this is n times the variance, the variance of the sample mean plus the sample mean squared, like that. Okay, so I got 1 over n minus 1. Then I got n sigma squared plus n u squared minus sigma squared plus n mu squared. Okay. N mu squared, that's an n. Okay. There we go. And that was a minus sign. Oh, so many things. Okay, yeah. So that minus sign was here, and that n was that n back there. Okay, sorry, almost done. 1 over n minus 1. Let's see, so we got this guy canceling that. Then we got n minus 1 sigma squared, and so that's sigma squared. All right, so in conclusion, the sample variance is an unbiased estimator for the sample variance. Okay, so what if you have an estimator that is biased? Well, let's talk about that. So if theta hat is an estimator, point estimator for a parameter theta, we define the bias. Let me just say definition. The bias of theta hat as an estimator for theta is the difference between the expected values, and we call it b sub n of theta. This is the difference between the expected value of our estimator theta and the value of our parameter. Okay, so the point is that this might depend on the actual value of the parameter. So for particular values of the parameter, maybe this difference is actually 0. Maybe you'll do well, and others maybe you won't do so well. So for example, this is really a silly example. Let's say we have a Bernoulli population with parameter theta. So in other words, the probability that our random variable is equal to 1 is theta, and that's 1 minus the probability that our variable has value 0. Okay, so just 0 and 1 with those probabilities. So what estimators might we choose? So a good estimator would be x hat, because of course the expected value is the expected value of x hat is the mean, and that is this parameter theta, right? That's the Bernoulli parameter. Maybe a not so good estimator would be like, well, I guess the coin is probably fair. Let's just guess that it's a half. So not great estimator would just be to say, just the constant a half doesn't depend on what observations I make. I'm just going to guess that the parameter is a half. Okay. So in that case, the bias of that is going to be the difference between the expected value, which is just the value itself because it's a constant, minus the value of the parameter, right? So there we get a bias that, of course, depends on the value of the parameter and doesn't depend on the n, how many observations we make, because it's just always a constant. Okay, so how about another example? We could consider maybe not a Bernoulli population, but just some general population with some, distribution. And we might think about theta hat as, so I'm going to estimate the variance, but let me estimate the variance by, instead of looking at the sample variance, I'll use the other denominator. So I equals 1 to n xi minus x bar squared divided by n instead of n minus 1, right? So then what do you have? I mean, the expected value of this, well, we worked out the expected value of the variance, and so of the sample variance, so we can just compare. So I'll pull out an n and put it in n minus 1, and I can write it like that, right? And then the expected value of s squared is the sample variance, as the population variance. And so so what we have is that as an estimator for sigma squared, the bias of this thing is, well, so it's it's Bn of theta. Theta in this case is sigma squared, and that's the expected value of this guy minus sigma squared. So that's what, negative an nth of sigma squared. So in this case, we see that there is a bias. On the other hand, if n is large, that bias gets smaller and smaller. So note, limit as n goes to infinity of this bias is is 0. And that's a useful property. It just says that your bias goes to 0 as n goes to infinity. So we say an estimator theta hat for a parameter theta is asymptotically unbiased if the limit as n goes to infinity of the bias is equal to 0 for all values of the parameter theta.